All right, thanks for joining me today. In the last video, we talked about the kinetic molecular theory and our different temperature scales. In this video, we're going to talk about the gas laws, how gases behave, and the laws of physics and chemistry that we use to describe those. So we're going to get into talking about those gas laws. But before we get into that, we need to talk about the gas properties. Certain things that we are going to use to measure to talk about gases. So the first property that we need to define is volume, and it's represented in equations with a capital V. Now, the definition of volume is pretty simple. It's the amount of physical space that a gas occupies, so how much space it takes up. Now, generally, when we're dealing with our situations, our equations, our experiments, and all of our calculations, generally volume is told to us by the size of the container that the gas is in. What is containing the gas? The volume of that container is the volume of the gas, because as we talked before, the gas volume will take up the volume of whatever its container is. Now, so the gas volume is determined by the container it's in. Now, gas is typically measured in liters. The volume is typically measured in liters. Sometimes you'll see it in milliliters or cubic centimeters, but most of the time we're going to measure the volume in liters. The second gas property is pressure. So pressure is represented by a capital P. So what pressure is a measure of the force per unit area that gas exerts on the walls of a container. So what causes pressure is all of those particles of the gas as they're flying around. Remember the kinetic molecular theory, they're flying in straight lines until they hit something. Well, the walls of the container are something that it hits. And when they hit it, they apply a force to that wall and push that wall out. Just like if I take a baseball and I throw it up against the wall, that baseball is going to apply a force to the wall. Well, if you've got millions and millions and billions of these little particles that are constantly hitting the walls, they're going to be pushing out on that wall. And that is the pressure. It's the force per unit area of the gas pushing on the container. That is what gas pressure is. It's all of those collisions with the wall. The common unit is the atmosphere. Now that's not the SI standard base unit, but it is the one that is most commonly used, is the atmosphere. And the atmosphere is defined as the pressure exerted by Earth's atmosphere at sea level. That's why it's called the atmosphere. It's the pressure of Earth's atmosphere. Now other common pressure units are the Pascal, named after Blaise Pascal, and this is actually the SI standard unit. So if I ever ask you what is the SI unit for pressure, the SI unit is the Pascal. But the Pascal is a very, very small unit. So if we used Pascals as our measurement, then we'd be dealing with really huge numbers because the Pascal is a small unit. So we don't usually use the Pascal, we usually use kilopascals or 1,000 pascals. Then here we're also very familiar with pounds per square inch, or PSI. That's what it's, how many pounds, because pound in the British imperial system of measurement, which we for whatever reason still use here in the United States a lot, the pound is a measure of force. So pound per square inch is the force per square inch, so it's force per unit area. And then we have millimeters of mercury. This one is used mostly in meteorology because that's what was used to measure atmospheric pressure sometimes. And this is how a barometer works. So it's called millimeters of mercury because the barometer, or something that measures atmospheric pressure, is basically originally were a little pool of mercury, and as the atmospheric pressure pushed down, it would push mercury up a tube. And so how many millimeters the mercury rose was the measure of pressure. So that's why it's called millimeters of mercury. And so they actually use liquid mercury in these barometers. We don't use mercury anymore because we now know that it's kind of hazardous to human health, and so it's not usually used, but that's where the unit comes from, and that's what it is. Now there's also a very old thing called torr, which was basically what they called millimeters of mercury before, but it's basically the same unit. So millimeters of mercury and torr are basically the same thing, they just have slightly different names. Now when you're converting pressure units, which you're going to have to do sometimes, because sometimes we measure the pressure in one unit, but to do our calculations we need it in another unit, so we're going to do our conversions and use our unit conversions properly. when you're converting them, we have all these different conversion factors. Now, since atmospheres is the most common, that is why I'm going to relate all of the other ones to atmospheres in our conversion factors. So 1 atmosphere is equal to 760 millimeters of mercury. And 1 atmosphere is equal to 760 torr, because torr and millimeters of mercury are basically the same thing. Then you have 1 atmosphere is 101.3 kilopascals, or 1 atmosphere is 14.7 pounds per square inch. I want you to think about that. The atmospheric pressure exerted by Earth's atmosphere on you is 14.7 pounds per square inch. Now, a square inch is like roughly the size of the tip of your thumb. So think of how many square inches of surface area you have on your body, and there's 14.7 pounds pushing on every single one of those square inches. That's a lot of actual pressure or force that your body withstands just because we're sitting in a fluid of gas. And then, of course, the Pascal, the SI unit standard, 1 atmosphere is 101,325 pascals. So this is why we don't really use Pascal, because to deal with something at 1 atmosphere or normal pressure, you're going to be using 101,000 is a huge number. So that's why we don't usually use pascals. So we've talked about volume and we talked about pressure. Now the next gas property that we need to deal with is the amount of gas. How much gas do you actually have? This is different than volume. Volume is how much space it takes up. Amount of gas is how many actual gas particles we have. How many gas molecules do we deal with? We represent that with the letter N. And we use the letter N because it has to do with number of moles. So amount of gas is a measurement of how many gas particles you have, and we measure it in moles. That's why we have gone through all of that mole conversion stuff and all that. The last one is temperature. Now, we spent a lot of time in the last video talking about the different temperature scales and what temperature is. Well, in our equations, temperature is represented with a capital T, and it is, of course, the measure of the average kinetic energy of the particles of the gas. Now, for gas law calculations, temperature cannot be a negative number. So because temperature cannot be a negative number in our calculations, we have to use kelvins, because the Kelvin temperature scale cannot be negative. And this is one of the reasons why the Kelvin temperature scale was developed, was to make the math work out a whole lot better and work out easily and fit the data that we were collecting in labs. And so we have a temperature scale that cannot be negative, and so we have to use kelvins. All of these gas law equations that I'm about to go over, they do not work correctly if you use Fahrenheit or Celsius. So regardless of what temperature unit you're given, you have to convert it to kelvins before you can do any of our calculations. So let's talk about these laws. We're going to call these the named laws because they each are named after a scientist. So the first one here is Dalton's law, and it's Dalton's law of partial pressure. And it is exactly what it sounds like. It deals with the pressures of parts. So what it states is that the total pressure exerted by a mixture of gas is equal to the sum of the pressures of the individual gases that make up that mixture. So the air that we breathe is not just oxygen, it's actually mostly nitrogen, a little bit of oxygen, a little bit of carbon dioxide, and a few other gases in there. Well, if I take a sample of it, I can pull out the nitrogen and measure the pressure of just the nitrogen. I can measure just the pressure of the oxygen, measure just the pressure of the carbon dioxide. And all those individual pressures added together make the total gas pressure. That's Dalton's law of partial pressure. And its equation looks like this. P total, so the total pressure of the gas, is equal to P1 plus P2 plus P3 plus ... So if you have 5, 6, 7 gases, you just go on. And so what this means is we're basically just going to add up the individual pressures. Now, one very, very, very important note about this equation is that in order for it to work, your pressures must all be in the same unit. So if I want the total pressure in atmospheres, all of my other pressures have to be in atmospheres. If I give you 6 pressures in kilopascals and I give you 1 pressure in millimeters of mercury, you're going to have to convert your millimeters of mercury into pascals or kilopascals before you can add them all together. They all have to have the same unit of pressure, or this equation doesn't work. So it's very important that you remember that, make a note of that, star it in your notes. But make sure that you remember your unit of pressure has to be the same for all of your pressures in order for Dalton's equation to work. So let's look at an example problem of Dalton's law. All right, so a container holds a mixture of gases at various pressures. Oxygen is at 320.0 kPa. So oxygen is at 320.0 kPa. Carbon dioxide is at 870.4 kPa. So carbon dioxide is 870.4 kPa. And nitrogen is at 3.05 atmospheres. So nitrogen is at 3.05 atmospheres. What is the total pressure? So my P total is what I'm looking for. So I know that my total pressure is simply the sum of all those pressures. But I do know that I have to have them all in the same unit. So since these are already in kPa, I'm going to leave them in kPa and just convert this one from atmospheres to kPa. So I have to convert 3.05 atmospheres, I have to convert that to kilopascals. So 1 atmosphere is equal to 101.3 kPa. That's one of the conversions that I just gave you. So we simply have to multiply those together. So 3.05 times 101.3, and that gives me 308.965, but I need only 3 significant figures, so that'd be 309 kPa. Okay, so now I'm going to add these together. Now we're going to do something that we haven't done in a while, and that's adding with significant figures. So I've got 320.0, 870.4, and 309, and these are all my kPa, kPa, and kPa. So I'm simply going to add all those together. So 309 plus 320 plus 870.4, and that gives me 1,499.4 kPa. But since we have just added them together, when you add, remember, we go by decimal places. So there's 0 or 1 decimal place, 1 decimal place, 0 decimal places. So I need to round this to 0 decimal places. So my final answer is 1499 kilopascals is my total unit. The point for this problem, though, is for Dalton's law is really simple. You simply add up the partial pressures to get the total pressure of all of them. All right, so now we're going to get into the second of our named laws, and this is Avogadro's law. We mentioned Avogadro's law briefly when we first started talking about moles, because that's Avogadro's law is what led to the development of the molar volume that we've been using in our discussion of moles. And because of Avogadro's law, we have honored Alessandro Avogadro with the name of the number 6.02 times 10 to the 23rd is now called Avogadro's number. But what Avogadro's law actually tells us is that if the pressure and temperature of a gas are held constant, then the volume of gas is directly proportional to the amount of gas or the number of moles. That should make pretty good sense to you. I have a balloon, and it's partially filled up. Now, if I were to take this balloon and I add more molecules to it, I added more molecules of air, and so the volume got bigger. It is directly proportional. If I double the amount of air molecules, then I'm going to double the volume. Now, if I let some of those air molecules out, if I decrease the number of moles, then I'm going to decrease the volume. And that is what Avogadro's law tells us. It's directly proportional. Volume and number of moles are directly proportional to each other. And so we have the equation V1 divided by N1. And we use divided by when we're talking about a direct relationship because it's a ratio. And in order for that it to be a direct relationship, that ratio has to stay the same. So if I double volume, I have to double N. So V1 divided by N1 is equal to V2 divided by N2. So we have a proportionality, and that is what directly proportional looks like mathematically. Is you're going to look at these two fractions. You basically have a proportion. Your initial volume divided by your initial number of moles is going to equal your final volume divided by your final number of moles. Those ratios have to stay the same. And so we have a graph here that shows a volume and number of moles. Anytime a graph or anytime two variables are directly proportional, you're going to get a graph that looks like this. It's going to be a linear graph, a straight line, linear graph that goes through 0, 0. In order for it to be a direct relationship, the graph has to go through 0, which means if you have 0 particles, you're going to have 0 volume. And that just makes sense. If there's no gas particles, then there doesn't be no volume of the gas because there's no gas particles. So a direct relationship has to go through 0. What that means is when one thing is 0, the other variable is also 0. That is a direct relationship. So let's look at an example problem of Avogadro's law and see how we would use this equation in a situation. So a weather balloon is filled with a gas to a volume of 39.85 liters. So that's going to be our V1. Our initial volume is 39.85 liters. To do this required 2.1 moles of gas. So that's N1 is 2.1 moles. If the pressure and temperature are allowed to remain constant, so I like to write this down, so I have pressure and temperature are constant. I like to write that down just to remind me that they don't change. What would the new volume of be if 0.75 moles of gas are removed from the balloon? Okay, so my new volume is what I'm looking for. It says what would be the new volume, so that's my question mark. If 0.75 moles of gas are removed. Okay, so I have 2.1 moles and I'm going to remove 0.75. So I subtract 0.75 from this, and that tells me that I have 1.35 moles of gas are my new number of moles because I removed 0.75. So we subtract that from here to get what our new volume is. Now, when we look at the Avogadro's law equation, is V1 divided by N1 equals V2 divided by N2. All right, and so this is simply a proportion. So we're going to solve this just like we would any other proportion in math. So I'm going to cross multiply. I'm going to multiply these two together and I'm going to multiply these two together, which is going to give me V1 times N1, or N2, sorry, V1 times N2 equals V2 times N1. So I cross multiplied, and now if I'm solving for V2, I need V2 to be by itself, so I want to move my N1 over here, and I'm going to do that by dividing both sides by N1. And that gives me an equation of V2 is equal to V1 times N2 divided by N1. So now that I have my final equation, because I did my algebra, I solved the problem, and I have my final equation, now I can plug in my numbers. So V2 is going to be 39.85 liters times N2 is 1.35 moles divided by N1, which is 2.1 moles. Now you'll notice that I didn't convert, when I did this subtraction, I didn't round this one to significant figures because I noticed that this was more significant figures than this one. And my final answer is always going to be the fewest number of significant figures. So I didn't bother rounding this one. I'm going to round at the end. Okay? So I know that I'm going to have two significant figures. But let's go ahead and do this math first. That's going to give me V2 is going to equal, so I do my calculator, 39.85 times 1.35 divided by 2.1. And that gives me 25.61785714. But I need only two significant figures because that's the smallest number of significant figures in my problem is 2. So I need two significant figures. So that's going to make this, instead of 25.6, it's simply going to be 26. And our unit is liters. Okay, so you'll notice a direct relationship means that my volume decreased because my number of moles decreased. If one goes down, the other one goes down as well. So this is just an exercise in doing a little bit of algebra and then plugging in the numbers. Now, Boyle's law is a very important law for divers and people like that. Boyle's law relates pressure and volume. So what it says is if the temperature and the number of moles of a gas are held constant, then the volume of the gas is inversely proportional to pressure exerted by the gas. Inversely proportional means as one goes up, the other goes down. If I increase the pressure, I'm going to decrease the volume. So if I push on something, it's going to get smaller. If I push on a gas, I increase the pressure on the gas, then I'm going to decrease its volume. If I decrease the pressure, then I'm going to increase the volume. Or if I increase the volume, the pressure exerted by the gas is going to go down. If I decrease the volume, the pressure exerted by the gas is going to go up. So it's an inverse relationship. The equation for this, if a direct relationship is a proportionality, I divide them, then a inverse relationship is you multiply them. So we have P1 times V1 equals P2 times V2. P1 V1 equals P2 V2. This is Boyle's law. And so what that means is the product, not the ratio, but the product of P and V has to stay the same. So if I double P, I have to cut V in half in order for the product to stay the same. So if one goes up, the other has to go down in order to keep the product constant. Now, a graph of an inverse relationship is going to look like this. It's going to look like a curve. And so you're going to have it where you have an asymptote at the zeros, the axes. So you're going to have this downward curve of an inverse relationship. And so this is the graph of Boyle's law and the equation for Boyle's law. So let's look at an example problem dealing with Boyle's law and diving. Okay, so 30 meters underwater, the pressure is approximately 4 atmospheres. So this would be my pressure at the beginning is 4 atmospheres. The average human's lung can hold 6 liters of air, so volume 1 equals 6 liters. If a diver fills his lungs to capacity at 30 meters, so that means this volume and this pressure go together because they're both at 30 meters under the water. And I realize that filling your lungs to capacity when you're that deep underwater is actually not physically possible. I understand that, but this is just for an example of this problem. And then returns to the surface without releasing any air, so that means the number of moles stays constant. We don't release any air. What would be the volume? So the new volume is our question at the surface. All right, so our new pressure is 1 atmosphere. All right, because pressure at the surface is 1 atmosphere. So we have pressure, volume, pressure, volume. So P1 times V1 equals P2 times V2. So to solve for V2, I need to get V2 by itself. So I have to move my P2. So I'm going to divide both sides by P2. And that makes them cancel out over here, and you're left with V2. So V2 equals P1 V1 over P2. So then I can just plug in my numbers. So P1 was 4 atmospheres, V1 was 6 liters, and P2 is 1 atmosphere. And I didn't point this out on the previous example, but you'll notice that atmospheres cancel, the unit you're left with is liters. So what this means for you is it does not matter what the unit of pressure is as long as they are the same. Same thing with the volume. It doesn't matter what the units of volume are as long as they are the same. So 4 times 6 is 24. So that gives us 24 liters. But we do want to stick with significant figures, and all of the numbers in my problem only had one significant figure. So I need this to only be one significant figure. So that's going to be 20 liters. So this is why you should actually exhale if you're down deep and you breathe in with your breather and then you come up to the surface. You should exhale or breathe out, because if you keep all of that air in your lungs are going to expand as you reach the surface and they'll burst, and that's bad things, and bad things happen to you, and that's not good. So you have to actually exhale as you ascend in the water. So that's Boyle's law. Now, the third named law that we're going to talk about is Charles' law. Charles' law is going to relate volume and temperature. So what Charles' law tells us that if the pressure and the amount of gas are held constant, then the volume of the gas is directly proportional to the absolute temperature of the gas. And this is the law that was actually used to develop the Kelvin scale. And you saw that graph in the last video, and so we're going to see it again. But they're directly proportional. As I increase the temperature, the volume is going to increase if we keep the pressure and the amount of gas the same. So increase the temperature is going to increase the volume. As I get heated up, it's going to expand. As I cool it down, it's going to contract. And so you're going to have a change in volume based off of that change in temperature, assuming we keep the amount of gas and the pressure constant. So the equation V1 divided by T1 is equal to V2 divided by T2. Again, this is a direct relationship, so the ratio has to stay the same. Now, if we graph it, you'll notice the graph on the left is using temperature in Celsius. And if you have the temperature in Celsius, then your graph does not go through 0, 0. You don't have 0 volume when you have 0 temperature if you use the Celsius thing, and that would not be a direct relationship. Remember, a direct relationship has to go through 0. When one variable is 0, the other variable is 0. This was a problem with the Celsius scale, and this is why the Kelvin scale was invented. If you look at the graph on the right, you notice that the graph does go through 0, 0. When you have 0 volume, you're going to have 0 temperature. When you have 0 temperature, you have 0 volume. Now, the left graph is a linear graph, but it is not a direct relationship because it does not go through 0. So this is why we had to come up with a relationship that showed it going through 0, because we saw the relationship between volume and temperature, and we needed to not be negative. So this is Charles' law. Let's look at an example problem dealing with Charles' law, and then we'll move on. An empty soda can holds 0.355 liters of air. So that's a volume. It gives us liters. So volume 1 is 0.355 liters of air. And that can is heated to 99.0 degrees Celsius. So T1 is 99.0 degrees Celsius. And then sealed, so no air can leave the can. So if the can is plunged into a bowl of ice water, so its temperature is going to change, obviously. And the temperature is rapidly reduced to 4.00 degrees Celsius. So that's 4.00 degrees Celsius. What is the new volume? So now I want to know the volume of the gas. Okay. Before we do anything else, we need to understand and we need to realize that our temperatures are in Celsius. And when we are doing gas laws, your temperature has to always be in Kelvin. So I have to add 273 to both of these in order to make them kelvins. So 99 plus 273. So this is 372 kelvins, and 273 plus 4 is 277 kelvins. So these are the temperatures I have to actually use in my equation. We have to have the temperatures in kelvins when we use gas laws. Okay, so Charles' law equation is V1 over T1 equals V2 over T2. So again, this is a proportion, so we're just going to cross multiply. We multiply these together, we multiply those together, and that gives us V1 times T2 is equal to V2 times T1. And now if we're solving for V2, again, we're going to divide both sides by T1 in order to get them to cancel out on this side. So I have an equation of V2 equals V1 times T1 divided by, times T2 divided by T1. All right, so now I can plug in my numbers. 0.355 liters times T2 was 277 Kelvin, and T1 is 372 Kelvin. So you'll notice that your kelvins are going to cancel. So we're going to pull out the calculator here, and 0.355 times 277 divided by 372 gives us an answer of 0.264. So I have three significant figures, three significant figures, three significant figures. So my answer needs to have three significant figures. So my answer is going to be V2 is equal to 0.264 liters with my three significant figures. So again, cross multiply, divide, plug in my numbers, round to proper sig figs. It's just plugging into the equation, not super complicated. The last law that we're going to talk about here is Gay-Lussac'S law. And Gay-Lussac'S law basically states that if the volume and the amount of gas are held constant, so we have a fixed volume and a fixed amount of gas, then the pressure exerted by the gas is directly proportional to the absolute temperature. So again, we have a directly proportional relationship. So we're going to have an equation that is going to be fractions. So P1 divided by T1 is equal to P2 divided by T2. And again, it's a direct relationship, so we're going to have a graph that looks like this. It's going to be a linear graph that goes through zero. So when I have zero temperature, I'm going to have zero pressure. Because if zero temperature on the Kelvin scale means that there's no molecular motion, then there can't be any pressure, because pressure is caused by particle collisions. Well, if they're not moving, they can't collide, and therefore you have zero pressure when you have zero temperature. And that is the basis of Gay-Lussac'S law, is that the pressure and the temperature are directly proportional. This is why you don't want to stick a can of hairspray in a fire, because that can of hairspray, the metal container, has a fixed volume and there's a fixed amount of gas in there. But as you heat it up, that gas is going to increase in pressure, and eventually that pressure is going to be too great for the metal container and it's going to burst and you're going to have problems. It would explode. That's why they tell you not to heat them or not to store them in a hot place, because as they increase in temperature, the pressure increases and then they could explode if the pressure gets too great for the container. So let's look at an example problem and actually put some numbers to the situation that I just mentioned. So a rigid propane tank holds about 18 liters of propane. When the tank is at room temperature, 298 kelvins, so that's going to be my initial temperature, 298 kelvins. It is under a pressure of 150.0 psi. So my pressure 1 is 150.0 psi. The pressure required to burst the propane tank is 1150 psi. So I'm going to call that P2 is 1150 psi. what temperature in Celsius would we have to heat the tank for it to burst? So T2 is what we're looking for, and we need to make sure we need to know that it has to be in Celsius. Okay, so what is the Celsius temperature? But it has to be in Kelvin to start off with. So we're going to simply plug into our equation of P1 over T1 is equal to P2 over T2. And just like all of the others so far, we are going to cross multiply, giving us P1 times T2 equals P2 times T1. And then we are going to solve for T2, means we're going to divide both sides by P1. Divide both sides by P1 so that the P1s will cancel out on this side, leaving us with the equation of T2 is equal to P2 times T1 divided by P1. So then I can simply plug in my numbers. So P2 is 1150 psi. T1 is 298 Kelvin. And P1 is 150.0 psi. So I do that in my calculator. I do 1150 times 298 divided by 150, and I get an answer of T2 is 2,284.6, and that's in kelvins because the psi are going to cancel and you're left with kelvins. My question wants it in degrees Celsius, so I have to convert that to degrees Celsius. So to do that, I simply subtract 273. So minus 273, and I get an answer of my T2 is going to be 2011 degrees Celsius. Now, this is 4 significant figures. My question gave me 3 significant figures here, 3 significant figures here. So I need to have 3 significant figures. So this would actually round to T2 being 2010 degrees Celsius. That's really stinking hot, and I don't know for sure, but I'm pretty sure that the metal of the propane tank would probably melt before that pressure or temperature would be reached to cause it to burst. So it would probably bust open before that when the temperature or when the propane tank melts. So there you go. There's that problem. So you've seen the different properties of gases. We have volume, we have pressure, we have number of moles, and temperature. Those 4 things are what we're going to be measuring and talking about their relationship. And some of them are directly proportional, some of them are inversely proportional. In fact, there's only one relationship there that we talked about that was an inverse relationship. It was Boyle's law, where pressure and volume are inversely related. The other laws are all direct relationships, so that's important that you remember that. And remember which things are constant and which things are changing in each law. We'll discuss that more as we move forward. But these 4 named laws, I often sometimes call them the alphabet laws because it's Avogadro's A, Boyle's B, Charles C, Dalton's D, and then we skip a couple letters and go to GAY-LUSSAC'S. So we have A, B, C, D, and G. So it's the alphabet laws. And so we're going to talk about those and use them moving forward. So make sure you know the definitions, know the units, know the terms, and pay attention to those equations as we go forward and talk about how we're going to use these in our different situations. Thanks for watching, and have a day.